To enrich the discussion, we have included a reading recommended by Lorenzo, which is Quality Control and Class Reduction of Satellite Images. I will share with everyone the link for this reading, okay? And we are very pleased to have today with us Sophie Bontemps from the University of Louvain. Not sure if it's the correct pronounce, Sophie. And Lorenzo, once again from FAO. They will present successful methodologies for us, and we encourage you to participate, ask questions, and use this space to think critically about how to adapt those approaches in your countries, in your needs. Okay, let's begin. Let me turn the floor to Lorenzo.
Thank you, Paulo. Thank you, everyone. And I will just briefly introduce this presentation, and then I will leave the floor to Sophie Bontemps. So I just would like to mention two things, that today's presentation is going to focus on Zimbabwe, as this is one of the countries where FAO, in partnership with University of Louvain, is working with the countries, with the NSOs and Ministry of Agriculture, to build capacity in the use of Earth observation data for official statistics, agricultural statistics. And the process has been so far very successful and has been articulated on different aspects. So we won't be able to cover all of the aspects. Those aspects also include field boundary delineation, drought mapping, and crop and flood mapping, and of course the crop type mapping integrated with the in situ activity. So the presentation is going to focus on these parts. I just wanted to say, that this is a part of a larger effort. And I also would like to spend one word on University of Louvain, and particularly on Sophie Bontemps and Pierre Deforny, because FAO has established in the past a memorandum of understanding with the university. So we have a long established collaboration at large, but specifically on the work of use of Earth observation data for agricultural statistics. Now we've been focusing since 2019, and we've been able to scale up to almost 20 countries. So we are very pleased with the work of University of Louvain, and therefore I will stop here and leave the floor to Sophie. Thank you very much.
Thank you, Lorenzo, and thank you for the nice introduction. Good morning, everyone. It's a pleasure for me to be here today for talking about the integration of remote sensing data and in situ data for the statistics. I hope the connection will be nice, because I'm in a mission in the Philippines, so in the other part of the world. So I hope it will be okay. I will share my screen. Okay. So as it was mentioned, so the focus of my talk is about the integration of satellite and field data for agricultural statistics. And the presentation will be organized in two main parts. First, I will spend roughly half an hour to present you the concept of this integration and a tool that was developed for this purpose. And then I will have another half hour presenting you concrete examples on how it works and with results. And as Lorenzo mentioned, it will be in Zimbabwe, but also in Spain. So I don't need to remind you the importance of agricultural statistics. You know it as well as me, even if it's not better. So agricultural statistics are much useful, of course, for monitoring agricultural policy, but also for an informed food security planning and sustainability assessment of the agriculture. So there are a lot of applications related to the statistics. Without using remote sensing data, So the way of computing these statistics is based on survey. So National Statistics Office are designing a sampling frame based on a stratification of their country. This sampling frame can be an area frame, a list frame, a point frame, and on this basis, they identify areas that need to be visited on the ground. They send enumerators throughout the country once a year or several times during the year, depending on the country, and these enumerators collect data. These data are quality controlled at the office, and these quality control data are used for producing the official statistics, which are published through bulletins or through official reports. So this is how it works without remote sensing data. And now we think that remote sensing data can be nicely nicely complement this field survey approach for crop monitoring, but also for estimating the statistics. So here, the focus is well on the complementarity between the remote sensing data and the field data. So we do not foresee that remote sensing will replace the surveys, but they will come in addition to these surveys to improve the statistics. And I will develop this concept a bit later in the next slide. So before doing that, I will focus a bit on the satellite data. In my presentation, I will talk about the European satellite missions. So more specifically, the Sentinel-1 and the Sentinel-2 from the Copernicus program. Why did I select these two missions? Because they perfectly match the agriculture requirements for agriculture monitoring in most of the countries. So we have these data which are open, free. So you have a redundancy in the satellite, meaning that you will always get images from these two missions. And there is a long-term continuity, which is ensured by the European Commission. So the budget is there, and you are sure that there will be satellites even not only now, but also in 10 years, 20 years, 30 years from now. So the conditions from the technical point of view and for the implementation point of view really allow operational applications like the support to national statistical offices. I will start with a quick animation about the Sentinel-2 mission. So the Sentinel-2 mission is a constellation of 2 satellites which are imaging the world every 5 days at 10-meter spatial resolution. So it means that every 5 days, at the minimum, you are sure that one image of your place is captured. Of course, Sentinel-2 is an optical sensor, so it means that when you have an acquisition, it's not necessarily an observation that you can use, because you know that optical data, when there are clouds, the images are not useful. But still, 10-meter resolution is a perfect spatial resolution for crop mapping. So you can see here a SWAT, so an orbit of Sentinel-2, which is very wide, 290 kilometers. So you have a very consistent image of your area, of your region, of your country. And at the same time, you get the 10-meter resolution, which allows you seeing the parcel, so capturing what is planted at the parcel level. So this is very well needed for the agriculture monitoring. This is another example of the Sentinel-2. Here we are in Philippines at 2 different seasons. You can see here rice perimeter, and you can see the difference in terms of vegetation. So just getting this information allows you following the seasonality of the crops at parcel level. You can clearly see on these images that we can distinguish the different parcels, the individual parcels. At the same time, we have the 10 meters, and at the same time, we have the 5-day revisit that I was mentioning. And this 5-day revisit gets you also a very good density of images if there are not too many clouds. So this is an example. These are examples of NDVI time series in Zimbabwe, so the country in which we have been working with Lorenzo. And you can see for different crop, maize, sugarcane, irrigated wheat, or sorghum, you can see that the density of this Sentinel-2 observation is very well suited to monitor the growing cycle and so to be able to make the difference between the different crop types. So this was for Sentinel-2, and I would like also to refer to Sentinel-1. So Sentinel-1 is not an optical sensor, this is a radar sensor. So the radar sensor has the capacity to collect information even if there are clouds. So here you get one acquisition every 6 days, and each acquisition is useful. So at the end, even this is a radar, so this is less easy to use, less intuitive when you look at the image, but the density of the images makes it very useful to monitor the growing cycle of the crop in cloudy areas. So this is an example of a simple backscatter image, also on a rice perimeter in the Philippines. And you can, the different colors you see correspond to the different stages of the growing cycle of the rice, just to let you know, to show you the quality of this data. So clearly with the data that we have, we can do a lot for agriculture. So this is clear. In parallel of these new missions, we have now a lot of clouds. So the cloud technology is there. So we have the infrastructure to process this large amount of data. So this is a second aspect that allows really operational applications. And we have also another aspect, which is more related to the in-situ data. So the collection of in-situ data of good quality and in good quantity has always been a bottleneck for agricultural application with remote sensing data. It is still a bottleneck, but with the new technologies that we have now today, so tablets, mobiles, UAVs, mobile phones, this bottleneck is slowly improving, I would say. So we now have capacities to collect more data. On the international scene, we have also more harmonization between the systems, more guidelines, more recommendations, and we have also a lot more open source tools that allow processing the data for users that are not experts. And so all these components make that today what I call the basic agricultural layers with remote sensing data. We can get them quite easily, I would say, so in an operational way. And these agricultural products are, this is the list here, so cropland products, binary cropland non-crop map, crop type product, but also biophysical variables to monitor the crop growing, to monitor the agricultural practices also. And this makes that now we can really focus on more advanced application, like the yield estimation, the impact of the crop diseases, and also the agricultural statistics. And this is really where we stand here. And for this topic of the agricultural statistics, our team, in collaboration with other colleagues, have developed a tool which is named SEN4STAT, so Sentinel for Agricultural Statistics. And this SEN4STAT tool has really the objective to integrate remote sensing data and in-situ data to support better statistics. And so this is the tool that I will present you, the main concepts during the first part of the presentation before diving into examples. So this SEN4STAT tool is an open source toolbox that processes SAR and optical data for operational applications in crop monitoring and agricultural statistics at national scale. So it really means, I insist on these words, so national scale and operational. So it means that the tool is really able to make a complete crop monitoring in an operational way over the country throughout the season. So it is using Sentinel-1 and Sentinel-2, the two missions that I have presented at the beginning. It can also rely on Landsat data from the NASA. And so it processes these time series, and it is able to transform these time series, so to interpret this data in 5 different types of products, which are identified here. So the first one are cloud-free temporal synthesis. So these are the very nice images that I have shown you over the Philippines. And the same for SAR data. So it means that these are data that you can look at. There is no cloud, there is no gap, and you can really understand the landscape with these products. The second kind of products are time series of spectral indices or biophysical variables, so NDVI or leaf area index, that are really useful to monitor the crop cycles. That will be useful for the yield estimation, for instance, but also for the crop discrimination. And then the third product, which is the key product, especially for today, these are the crop type maps. These maps are done along the season based on in-situ dataset. And then we have the products 4 and 5, which are related to the yield estimation. So these are metrics that are explanatory variables about the yield, and then the crop yield estimation at different administrative units. So these are the 5 types of products that can be done with Cent4Stat. So the idea, as I repeat, because this is really important, the idea between this Cent4Stat is to first interpret the Sentinel data into different products using field data. We need field data to make a crop type map. And then when we have these EO products which are there, we integrate these products with the statistical survey to improve the statistics. And there are different ways of improving the statistics, which are listed here. And all this small bubble, I will explain it now. So the first application of EO data to improve the statistics is what I call the cost efficiency. So we will be combining the map with the ground data to decrease the confidence interval around the estimation. So we maximize the statistics accuracy without increasing the cost of the survey. So this is really the idea. The second one is to improve the granularity of the statistics. So by having a map, you can derive your estimates over small administrative units, which is something that is not always possible with a survey because the number of samples is limited. And so you can only compute statistics at the administrative level where you have enough samples. Remote sensing data can also increase the timeliness, so you can get data as soon as the season is over. It can also support an improvement or an update of the sampling design. So as I said, usually the sampling design of the survey is based on the stratification, and a lot of crop map products based on remote sensing data can be used to support this stratification. We also work on the quality control of the data that have been collected in the survey. This quality control can rely or can benefit from remote sensing data. And the last bubble is what I call downstream application. So statistics is one thing, but the statistics, the fact to know the acreage can also be useful for a lot of downstream applications, disaster management, early warning system, crop insurance, and so on and so on. So this is how we see the benefit of remote sensing data for the statistics. So this is not only the accuracy. Accuracy is, of course, very important. This is the first bubble, the first green bubble, but this is not the only entry point of remote sensing data in statistics. Just a quick overview of the Sen4Stat toolbox. So the way it is presented here. So all what is in blue is related to the processing of remote sensing data. I will really not go into detail today because this is not the purpose. So just very briefly, you download the data or you read it if you are working on the cloud. There is some pre-processing, cloud masking, backscatter, coherence computation, etc. And then you get one processor by type of products. So 5 products, 5 processors. And at the end, you get the 5 products that I have mentioned that you can visualize or use. The second module is the green one about the in situ data. So the in situ data need to be uploaded in the system to allow running the system. And they are a bit quality controlled by the system. And the last part of the Sen4Stat is what we call the analysis or the statistics, is how we interpret or we combine the products with the in situ data to improve in a way or another the statistics. So these are the workflow, general workflow of the system. I will focus on one aspect, one processor, which is the crop type mapping processor, because the crop type map is certainly the key product for the integration. These are very nice examples and easy to understand because a map is something visual. So this crop type mapping processor is organized in 3 components. The first one is the pre-processing, the preparation of the remote sensing data, Sentinel-2, Sentinel-1. Then there is the in situ data, which need to be present to make the map, and then the classification in itself. So you have a learning, a random forest or a neural network or whatever, a classification model that you train. And when it is defined, you apply it for the whole area and you get your crop type map that you validate. So nothing complicated, nothing special in that. What will be key in Sen4Stat is this component, the in situ data pre-processing. So this is basically all the survey that you do and that we need. So with this in situ data, what will we do in Sen4Stat? The first thing we will do is calibration. We need in situ data to learn, to train the algorithm, the classification model. So these in situ data that will be used for calibration have specific requirements to be sure that, to ensure or to allow your algorithms to be performant. These data need to capture the entire diversity of the cropland and non-cropland classes. So it means that all the land uses and land cover that are in your area of interest need to be present in the data that will be used for calibrating your algorithm. It needs to cover the full diversity of the crop types, even the minor crops, not only the main one. And the data need to be spatially distributed over your study area. These are the 3 main properties to get a nice in situ data set for calibration. So calibration is the first use of the in situ data. The second one is the validation. So we will use in situ data to estimate the map's accuracy with a confidence interval. And the property of this validation needs that they should be they should follow a sampling that is statistically valid. And they need to be fully independent from the data used for the calibration. So this is really important, because if this is not independent, what you validate is not the map, but what you validate is the classification model. And the third application, beside the calibration and the validation, is the statistics estimation. So of course, when you will get your map, if you want to improve the statistics, you will have to combine the map with a statistical survey. And I will explain how we do that. So basically, this is through a regression estimator, but it means that you also need data that come from a statistical survey with a sampling frame that is statistically valid. So maybe the in situ, it does not need that. This is what we will do with the in situ data. It does not mean that you need 3 fully independent data sets. No. What is sure is that data for validation shall be different than the data for calibration. Then data for calibration can be the same than for the statistics estimation, for instance. You just need to be sure that you capture everything what needs to be captured. I will show some example now. And so before the example, maybe something very important. So the prerequisite to be able to integrate EO data and survey, so to couple satellite images and in situ data, is that there is a geographic link between the image and the in situ data. So we need GPS coordinates at parcel level, not at the level of the households. So in many statistical surveys, the enumerators go to the fields and they make interviews of the farmer, and they take the GPS point of the house of the farmer, so of the farm, and then they visit the fields. This is not enough to be able to use remote sensing data. When the farmers say, I have 1 field of 2 hectares of wheat, of corn, we need to know where this field is to be able to make a link between the pixel, so the time series that we get from the image, and the crop type. So this is really important. This is really the prerequisite to do that. Then in terms of data collection, in Census, we can use data that come from existing agricultural survey. So statistical survey from National Statistics Office. This is an example here in Africa with the official statistical survey from the CPS, Cellule de Planification Statistique. We can also, not for the statistical aspect, but for the calibration, we can also say, okay, I do not have enough data in my statistical survey, and so I will do a windshield survey. Windshield means that you take your car, you go along the roads, and you take as many points as possible of all the classes. So no need to be statistically valid. The objective is to collect data of all the classes that I have in my country, because I need that to calibrate the algorithm. So these are examples of this kind of transact. Here it was in Ukraine, here this was in Uganda. So everything is possible in terms of windshield. You can use car, you can use motorbike, and this is probably the most easy type of survey that you can do. A last example of a survey that we did. This was in Pakistan last year. Here we have been working with the NSO in the Sindh province in Pakistan, and they had no. We started really from scratch. So there was no existing digital data collection. They did everything with papers and with interviews. And so we drafted an area frame survey, which are the statistical survey, which are the yellow square that you see here. So these units were the units that had to be visited for the statistical estimates. And between the units, when we were on the cars, we also collected points, through the windshield approach. And so at the end, this is the number of points that we collected. So a lot of freedom. We need to be creative. We need to be imaginative. In terms of data collection, what is important to have in mind is that we need data to calibrate, to validate, and of course, statistical survey for the statistics estimate. Then when we have all this data, we can do a map, a crop type map. So this is I follow with the example in Pakistan before going into Zimbabwe and Spain. So this is a crop type map, a wheat map, sorry, in different districts of the Pakistan based on the windshield data. So not the statistical data, the windshield data. This was done with a random forest. These are the specification, and this is the, let's say, validation that we obtained. So this is not something that is perfect. So we can see that the overall accuracy is a bit below 0.9, and the quality for the wheat is 0.85. So this is good, but not perfect. Then with this map, we try to estimate the acreage, so the wheat acreage, by integrating the map with the statistical survey. So when we do that, the objective is really to combine an unbiased information, which is the survey, with an information which is biased but spatially exhaustive, and this is the map. So in the map, all what is orange is my wheat, and in the survey, so the points that are orange are the points that have been identified as wheat on the ground, and the points that are in red are the points that have been identified as non-wheat on the ground. And so the combination, the integration will be done by a regression estimator. And so the principle is the concept is this one. So in the map, I get a bit more of the half, so 5,489 wheat pixel over the 10,000. So it corresponds to a 0.55. And the in situ on the survey, I get 9 points out of 15 that are identified as wheat, 0.6. I will calculate these proportions for all, if I come back to my illustration, for all the squares that I visited, my primary sampling units. So I will calculate the proportion for all of them, and then I can do a regression estimator. So I will quantify the map bias inside the primary sampling unit, thanks to this regression estimator. So I will, on average, know how much the map over or underestimates the wheat proportion inside my sampling unit. And when I know this bias, I can apply it over the full area. I can correct the bias of my map to obtain, thanks to my map, unbiased acreage estimates. And so in the end, this is what we obtained. So this is the acreage estimation for wheat. So the crop reporting service is the NSO. So we get a first estimation at the middle of the season, which was not associated with a confidence interval. A second one at the end of the season. And we also computed the wheat acreage only based on the statistical survey. So without remote sensing data, without integration. And this is the value we obtained. And here, with this inference, we could compute a confidence interval. So the three first estimations are without remote sensing data. With remote sensing data, I can compute an acreage estimate. In fact, I realized that I invert the legend of the bar. So the first bar here with no confidence interval is a simple pixel counting in my map with the bias removed. And so this is the value I get, but I get no confidence interval. And the second one is the regression estimator. And what I can see is that when I get this regression estimator, more or less, I'm in the same range of values that the official figures of the crop reporting service, and also of the inference from the statistical survey, but the accuracy is better. So the confidence interval around my acreage estimate is significantly reduced. And so this is a good result. This is one of the applications that I can have by using remote sensing data, is maximizing the accuracy of my statistics without increasing the cost of my survey. And with that, this is what we call the cost efficiency analysis. In fact, you can compare different approaches. And the approach, the cost efficiency approach, is based on the computation of relative efficiency. If you have one method, two methods to compare, you compute this relative efficiency by calculating how much you reduce the error between the two methods. And the same for the cost, the relative cost. So what is the relative price increase to obtain the estimate using the second method compared to the first method, and that you get your cost efficiency as the product of both terms. And if your cost efficiency is lower than 1, it means that the new strategy that you are testing is not worth the price. But if it's higher than 1, then it means that the benefit is higher than the cost, than the limitations. With that, I'm at the end of the first part of the presentation about the concepts. And so I will start the examples, the use cases in Spain and in Zimbabwe. I don't know if I need to stop for questions or if I continue when the questions come at the end.
I believe we should. I believe we can continue, Sophie. And
okay,
questions at the end, okay?
Okay, no problem. Okay, so let's start with the application in Spain. So in Spain, we have been collaborating with the National Statistical Office, and their survey is an integrated list and area frame survey, which is named ESIRSE. So you can see here, these are the primary sampling units. And inside these primary sampling units, we have polygons. So we have roughly 400,000 polygons at national scale in the year of the collaboration, so it was 2020. And this is how these polygons within the agricultural survey are distributed between the crop types, the crop classes, the land cover classes, sorry. So you can see that, of course, there is really a bias to crop, annual cropland and perennial cropland. This is obvious because this is an agricultural survey. So as a side note, to do our processing, we complemented this survey by external data for the non-crop classes because we did not have enough data, enough samples for the non-crop classes. We use an existing land cover map to increase the quantity of non-crop samples. But continuing on the statistical use case, so this is the crop type map we obtained at national level. So you can see here the different classes. So this is quite detailed. And this is the validation. So again, we had an overall accuracy which was high, but the quality of the classes were quite uneven. So of course, for the main classes, we performed quite good, but for the minor crops, it was not so good classified. And so on this is something that I want to stress. So for the moment, working with remote sensing data, we are able to contribute to the statistics for the main crops. So the crops that we can map well, not for the minor crops. This is a limitation we have to work with. And so based on this map, we did exactly what I explained before. So we did the regression estimator between the maps and the survey. So this is an example of this application and this example is on the region of Castilla y León. So this is an administrative level in Spain. This is the region which is the main producers of cereals. So very important from the agricultural point of view. So you can see here for the 3 main crops of the region, so wheat, maize, and sunflower, the impact of the remote sensing data. So how can you read this table? So you get one crop by color, the F-score of the crop, so how it was well classified, so the accuracy metric. And then for each crop, the first line is the accurate estimate you get using only the survey. eserse. And the second line is the estimate that you obtain when you integrate the survey and the remote sensing data, so the survey and the map. So for all the crops, when you compare the acreage estimates, you can see that it is more or less similar. Of course, not exactly the same, but more or less similar. So these estimates are associated to a confidence interval of 95%, and you can see the upper and the lower limits for all these estimations. The good news is that all the confidence interval intersect. So with and without remote sensing data, the confidence interval intersect. But the main result is, in fact, that the amplitude of this confidence interval is significantly reduced when you use the remote sensing data. You can see here, so almost by 3, even here by 4, the confidence interval is reduced. And so it means that the sampling error, and this is this column, but this is also reporting here in this graphic, is, of course, the sampling error is significantly reduced when you use the remote sensing data, which makes the efficiency very high. So when I was talking about the cost efficiency, you had to compute the relative cost and the relative efficiency. So here, the relative efficiency was very high because the reduction of the sampling error was very significant. So this was something that, of course, was a very good result and appreciated by the NSO. We tested the same for the yield. I did not went into detail in the slides below because the level of maturity is not the same. But I will present this application because we were able to get good results in Spain. So the way we work for the yield is that so we had some samples from the statistical survey where we had the yield. We are just for the moment developing a methodology. So it means that from all the samples we got, we used a certain part of the samples to calibrate a model that estimates the yield. So using these samples, this ground data with remote sensing data with meteorological data. And then we train a model and we estimate the yield on the samples that were removed. You can see, the arrow should go in the opposite direction. But so you have more samples on the right illustration because we have estimated the yield on new samples. And this is the kind of regression we have. So quite good results, quite nice regression. And so again, when we then compute the mean yield estimation over the district level, the result is more or less the same than with the crop acreage. So we are more or less in the same level of the yield estimate, which is quite good, but the standard deviation has significantly decreased. So again, the efficiency will be higher with remote sensing data. But this is still more at the development stage because for the moment we only worked with the data where we got sample. We did not yet apply it at full scale. So these are preliminary results, but still going in the right direction. The second use case that was done in space is the granularity of the statistics. So we were able to get reliable estimates over small administrative areas without increasing the sample size. So here we are not at the district, but we are even below. We are at the municipality level where we were able with the map. So by combining the map and the surveys to get accurate estimates, it is for the barley in this case. And the sampling error is acceptable. So the level of acceptance defined by the NSO was 20%, and in most of the cases we are below this threshold. And this getting the estimation at this administrative level, so at the municipality level, is not possible without EO. So it means that using the survey only, there is no enough samples to make a reliable estimate. So again, this is a good demonstration that the granularity of the statistics can be increased using remote sensing data. We also developed a product that was requested by the National Statistical Office to update their sampling frame. So far, the stratification of the country was based on crop intensity and on the distinction between annual and permanent crops. And they were interested in also getting information about the irrigation to be sure that they have a representative number of samples in the irrigated areas versus rain-fed areas. So we developed a methodology to make such a map. So independently from the crop type, we know we classify when it is rain-fed and when it is irrigated. And we validated the map crop by crop. So usually the results are quite good. For the crops that are significantly irrigated, like the maize or the citrus fruit trees, but also for the crops that are usually rain-fed. So this is a good news because there is no bias towards the practice. So for that, we worked with the statistical survey, of course, because in these surveys we had some information about the irrigation, and we work by crop type. So we developed a classification model between irrigation and rain-fed for each crop type. So for that, you need the crop type map. You can use the crop type map that has been done, that is generated by Cent4Stat, so you can use another crop type map. Here, we also tested another crop type map, which comes from the Common Agricultural Policy, but this is specific to Europe. And this is the kind of map, just to show you, that we get. And this map will be used for updating the sampling frame by the NSO. The last application in Spain that I wanted to mention is about the timeliness. So the objective of getting the advantage of working with remote sensing data is to increase the timeliness of the statistics. So to get them as soon as possible after the end of the season. So what we did is we validated the map as soon at a different moment in the season. So here this orange line corresponds to the middle of the season. And what you can see is that the accuracy reach a kind of maximum, a kind of plateau, as soon as 1 month after the mid-season. It means that the map, the crop type map, can be already used before the end of the season to derive, I would not say statistics, but to derive area indicators like the pixel counting estimator, removing the bias thanks to the confusion matrix. So this is a kind of information that you can get before the end of the season. And then as soon as the season is over, you get your map from the end of the season, because the time to produce the map from the remote sensing data is very short. And then as soon as the statistical survey is available, you can combine and you can integrate both sources of data. So Spain was chosen before Zimbabwe to show you, because this is a country where we were able to cover a lot of use cases. Then the second country is Zimbabwe. As Lorenzo mentioned, we have been working in Zimbabwe with FAO. So we are partnering with the Ministry of Agriculture in a specific project, which is part of the EOSTAT program. And the ambition, the objective of this collaboration is to develop a national crop monitoring system. So this national crop monitoring system is targeting the statistics, the monitoring of the crop, but also the integration with early warning systems for disasters management. So this is quite comprehensive. So we did first a pilot to better understand what was the reality in place. So just before we did a small test. We mapped the irrigated wheat, which is cultivated during the short season. So not the main one, but the short season. There was some data that were collected. And at the end, there was a winter wheat national map. From this experience, we learned that Sentinel-2 was really useful in Zimbabwe. It was suitable for the kind of agriculture we had there. So this was a really good news. the size of the fields were compatible with the 10-meter resolution, and there were not too many clouds, so we do not need Sentinel-1. So these were the two learning from the remote sensing point of view. From the in-situ data collection, we also learned that we had really to focus on the protocol to ensure that good and relevant data were collected. And so this is an example of the map. And so the first part of the collaboration focused on the in-situ data collection. And as I said, when we collected the data, we had two objectives in mind. The first one is that we need data to map the crop type, so to train the classification algorithm, but also data for the acreage estimation. And so the way it was designed is that there was a statistical survey, an area frame survey, to allocate to different segments throughout the countries. So the country was stratified, and we had this kind of primary sampling units, so squares with points randomly selected inside, and the points had to be visited by the enumerators. And between the primary sampling units, there was a windshield survey, so to collect many points across the roads, and these windshield would serve for the mapping purposes, so to train the classification algorithm. So the in-situ data collection was really carried out by the Zimbabwean team with the support of FAO. And at the end, this is all the data that were collected that you can see here. So we had 1,672 samples from the statistical survey and 2,900 samples for the windshield, which is quite few. I must say that this is something that we need to improve. And you can see here how the data are distributed between the land cover classes here and between the crop types. So of course, a clear dominance of maize, so a lot of classes that are not well represented. From the remote sensing data, as I said, we have worked with Sentinel-2 images covering the full season from October 2023 to July 2024. So we have 64 Sentinel-2 tiles, which makes a lot of acquisition over the season. And this is that was used to do the summer season crop type map at national scale that you can see here. So the accuracy of the main crops, maize, but also sorghum, millet, we were over 75. And the sugarcane, which is a crop that you can find only here in the southeastern part of the country, was also quite high. The crop is the map is far from being perfect. So as you see here, we had very few samples for the minor crops, and not enough samples in the windshield. So the grassland, for instance, there was a lot of confusion with the fallow, etc. So we know that there are a lot of things to improve, but the map is the map. And we try to combine it with the statistical survey in the same way as I explained. So before coming to the survey, these are some examples of the maps. This is the perimeters of sugarcane that I have just mentioned in the southeastern part of the country, here in blue. So again, you can really see the fields, the big fields of sugarcane. But if you look here in the smallholder agriculture, you can also see the fields limits. And here, this is another area of millets, basically. And again, the pattern of the landscape is clearly well defined. So coming to the statistics, so here again, we will combine the in-situ data with the map exactly in the same way as I explained before. So you count the number of pixels. Here, this is an example for the sugarcane in the map and the number of samples in the primary sampling units. And then you make the regression and the accurate estimation. And so here, these are area estimation for the maize, and for the maize grouped with the millet and the sorghum. And so this is the accurate estimate you get from the inference from the statistical survey with a given confidence interval on the left, and on the right, the regression estimator. And in both cases, you can see that the confidence interval is reduced. The reduction is less obvious than in Spain. So this was one of the small deception, I would say, of the project. So this was the first year of the project, and we are continuing. And this was clearly explained by the survey, where we did not have enough points, given the fact that we are working at national scale and that this country is quite big. But the main principle, the main concepts of the methodology were confirmed, I would say. And the second aspect that is worth to be mentioned is the timeliness of the statistics. So these accurate estimates for the main crops, so the crops of the summer season 2024, were available and presented to the NSO and the Ministry of Agriculture in November 2024. So quite a timely information for them. In Zimbabwe, so we have been also asked to couple the crop mapping and the accurate estimate with an early warning system to help in the management of the disasters. And so here we have developed a drought monitoring system, not from scratch, but we have, let's say, we wanted, in fact, to couple the map with drought maps. And the drought maps that are existing, and we took here the example of the FAO ASIS products, were all at core spatial resolution. So this is what you can see here. You had pixel of 1 square kilometers. And when we wanted to integrate our map, we say, oh, this is really a pity. We did the effort to do a crop type map and to have accurate estimates based on parcels, and then we just mix this information with coarse resolution. And so we did a test to develop, to get a draw information at high spatial resolution, to be able to have a draw monitoring at crop type level. And so there was a prototype that was done on one district of the country. And so in 2 slides, no more. So the principle of this draw index. So this is the draw maps are based on the vegetation health index. So there is a vegetation condition index and a temperature condition index. And so we combine both. Of course, when the vegetation is good, usually the temperature is good. But when you have a high temperature, you will have a low vegetation index. So this is a combination of vegetation and temperature that gives you the vegetation health index. And we just worked, as I said, with high spatial resolution. So the basic product was at 1 kilometer, and we have been working at 30-meter resolution. And this is what we obtained as a prototype. So this is the official product at 1 kilometer resolution and the prototype at high resolution for 2 different months. We can see that we find the same pattern, so red areas in the middle for January and red areas here all in the north for March. But we get much more red in the prototype. And so the good news was that really we could see the draw impact at the parcel level. So this is what is illustrated there. And then when we had this prototype, we could combine this draw map with the crop type map. So for instance, here, the sugarcane and the sorghum. And we can see that the draw impacts in a different way the 2 crops. Sugarcane was not really impacted by the draw, while sorghum was much more impacted. So you can see that there was really an impact here of the vegetation that was quite low. And then by getting the accurate estimates of this crop and knowing that the draw really impacts one specific crop and not the others, you can be much more precise in the decision you take, in the insurance, for instance, or in all the actions that you take for monitoring, for managing the draw. So this was a side result of the exercise we did with statistics, but just to show that statistics estimate is not only important for reporting, but it has also many downstream application. And I come to my last slide with some take-home messages. The first one is that remote sensing data can complement traditional statistical surveys. I'm convinced on that, and I think that the work we have been doing so far goes in that direction. The way the remote sensing data are useful to improve the statistics are diverse. The most expected way is to, of course, reduce the confidence interval, so increase the accuracy, maximize the accuracy of the statistics. But we have also shown that it can support a spatial disaggregation of the statistics and also a better timeliness. So here I have presented results in Spain and in Zimbabwe because I had only 1 hour allocated to this presentation, but you have to know that we are also working in other countries where there are other successful use cases. The other main message that is I would like you keep in mind after this presentation is the importance of the in situ data, of the survey data. So this survey data needs to be EO compatible. If you want to use remote sensing data, these data needs to have geographic coordinates at parcel level. This is a must, a shell. There is no other possibility. And then in the data that you collect, if you want to do a good map, you need to make sure that all the crop classes are well represented with a minimum quantity of samples, even for the minor classes. And also this data set must include the non-cropland classes. And last but not least, the data must be evenly spread across your area of interest, so to have a good geographic distribution. The results that I have shown you is based on the Senforstat toolbox. So this is open source. This is based on Sentinel-1 and Sentinel-2, and has been designed for agricultural statistics at national scale. So this is really the purpose. And the last one, and this is also an important aspect of pushing to the adoption of the remote sensing data as a new technology. So the uptake of this new technology by National Statistical Office, by Ministry of Agriculture, or any stakeholders takes a lot of time, and this is normal. This requires really capacity building. And there is a long-term vision that needs to be adopted with a step-by-step approach where you first do a demo, a pilot, and you upscale, and then at the end you reach the autonomy. But this is something that cannot be done in one project of 1 year. You need really to invest in all the aspects of capacity building and demonstration, convincing the people you are working with. And with that, I stop my presentation. I hope it was of interest for you. And you get here in the slides my email if you want, and the website of the Senforstat project and toolbox that I have presented today. Thank you very much.
Thanks a lot, Sophie, for the excellent presentation. I would like to start the question and answers session with a first question for you, which is, you have worked with different regions. How do you see challenges in Latin America compared with, let's say, Africa or Europe when it comes to Earth observation data integration?
I would say that it depends on the country, but certainly we have the cloud cover, which is an issue, and also the mountainous area and the hilly landscape. So why do I mention these two aspects? The cloud cover means that Sentinel-2 is in many countries is not enough. We need to complement with Sentinel-1 for some seasons. Not all the seasons, but this is needed. And also where you have mountainous areas, there is a drawback because the SAR data efficiency is a bit lower. So SAR and hilly landscapes are not good friends. And so in these specific areas, this is challenging, to be fully honest. But this is not EO for statistics. This is just EO alone. Using remote sensing data with cloud cover and mountains remains a challenge. This is one aspect for remote sensing data. The other aspect I could mention, but which is not really specific to Latin America, we also have sometimes this situation in Africa, is the fact that in Latin America, there are often multiple crops on the same parcel at the same time. And then in terms of mapping, if the parcel is small and there are multiple crops, it can also be complicated. I remember we have been working in Salvador, for instance. In Salvador, you could have small parcels with 5 crops. Then in this case, it's also a challenge with remote sensing data. But as I said, this is not specific to Latin America. In Africa, in some countries like Rwanda, for instance, we are facing the same challenge. And for this specific challenge, I would say that maybe the spatial resolution of Sentinel-2 might not be enough. So higher spatial resolution might be needed if we want to do a proper mapping.
Thanks a lot. There is a complementing question on the chat. Well, disappeared. So let's wait a little bit. Maybe the person will send it again. But taking the time, Sophie, what would you say is the most common mistake or misconception when people first try to combine satellite data with field data?
I would say that the first thing not to do is to do pixel counting. A lot of applications, you just do a map and you count the number of pixels of one crop and you say this area has an acreage of such an area. You count the pixel, you multiply by the area of the pixel. So this is certainly not statistics and estimates. So at minimum, you need to debias your pixel counting using the confusion matrix. And the best is then to really not deriving the acreage from the map only, but to combine with a statistical survey. When I say statistical survey, it's a survey with a statistical sampling design.
Okay, thanks a lot. Let me pass to Gilberto, who raised the hand. Good morning, Gilberto.
Good morning, bonjour Sophie, ça va bien?
Good morning, Gilberto.
C'est bien de vous voir. It's of course no surprise to me that you always give an excellent presentation. So first of all, congratulations. It's a very important work and a lot distilled, a lot of experience distilled in a few slides. I have 2 specific questions. One concerns what you do when you have a very imbalanced data set. Have you experienced rebalancing the data sets by some artificial sampling creation techniques? That's question 1. And then question 2, what would be your best estimate in terms of years, of course, and teams, if an NSO would like to be involved in remote sensing for agriculture statistics? I know I'm pushing this a bit, but I think you probably can give a let's say, rough figure for people in the room.
2 very good questions. It's not a surprise for me neither, Gilberto. So good to see you too. First question. So imbalanced data set, yes, we have tried some techniques with let's say artificial augmentation, synthetic augmentation of the sampling. For instance, we have tested the SMOT approach. So the fact that to be sure that everybody understands. So when you have a data set where for some classes you have very few samples, there are algorithms that will artificially increase the number of samples by creating artificial samples that mimic the samples that you get. So we tested it, and it has a positive impact, but you need to get a minimum number of samples by class. So if you apply such technique and you ask 100 samples based on 5, 6, 7 samples, you will in fact just not have enough data to create a good model. And then your artificial augmentation will in fact just create noise because it will not be reliable. And so in this case, it has bad impact. It's better not to augment if you do not have a minimum number of samples for the class. This is at least our experience. What we do also when we have a non-balanced data set is that sometimes we simply decrease the number of samples of the majority class, meaning that we take 50% of the samples we have. It's a pity not to use all the data we have because we know that getting data is really challenging, but sometimes it's also another good approach to improve the balance in the data set. So these are the two ways we are trying to do when we are in this situation. For your second question, this is a very good question. I think I would say if I have to give a rough estimation, I would say between 3 and 5 years. Saying let's say maybe not years, but 3 and 5 iterations, because sometimes you get 2 iterations by year if you get 2 seasons. But the way we are working with NSO for the moment, and we are not yet at the end because this is an activity that we started 2 years ago. So we are really in the process, I would say, is that first you start with a season where you do the job for them over a small area and you try to convince. And when they are convinced, I mean, you repeat over maybe you scale up a little bit, but this usually the first aspect you work with them is the survey. To optimize the data collection, to make it more remote sensing compatible, to add a windshield, because usually the statistical survey is only done. And when I say only, of course, this is just a way of speaking, because this is their job, but we do not have enough data for mapping. And so when we have really progressed on this data collection, then we start the training on the tool in itself, the remote sensing, because then they will not be really motivated to be trained on the remote sensing technology if they are not sure that it's worth doing the investment. So this is really important first to convince, to get them in charge when you do the training. And then when we do the training on the technology, we start by doing the processing at house, and they do it in parallel. And then the second time they do it themselves and we provide support. And the third time the level of support is minimized. I would say this is a kind of roadmap. It can be sometimes quicker, sometimes slower, depending on the country, but this is the idea. Lorenzo.
Thank you, Sophie, for the presentation. And I just wanted to contribute to the question asked by Gilberto on the, let's say, the timeliness and the sustainability, I would add. So as Sophie explained, the anchor of all of this is really having a robust protocol in place from the official mechanism in the country that collect crop data. And this is something that characterizes, I think, EOStat and differentiates from other initiatives that we have on crop type mapping, is that we are really trying to ensure that the mechanisms that are required to feed in situ data, they are statistically robust. And therefore, our entry point are really the NSOs and the Ministry of Agriculture, who are concerned with the data collection. That is I think, the most important point from the feasibility, to make sure the country is ready for uptaking geospatial. The other side of the story, I think, that is now also becoming more important is that when you look at the sustainability of the exercise in time, you might realize that you might have different teams working together, and probably those who gather the data might not necessarily be the ones who want to process the satellite data. Okay, so you might have a situation where the Ministry of Agriculture is now specialized in collecting the data, in having very good georeferenced in situ data, but then you can have also other institutions in the country who can collaborate and contribute to run the classification algorithms, for instance, and probably contributing to create those synergies when we deploy a project in a country. So gathering together the Ministry of Agriculture, the NSO, the Space Agency, and those who may also have a role in ensuring that a data cube, a national data cube is provided. This can, I think, also ensure the sustainability beyond the work at the field level that, of course, as we clarified, is fundamental, and we don't think will be substituted by remote sensing and AI, but it will just be augmented. Thank you.
There is one Ileana Camila, which is with the hands raised. Thanks a lot, Lorenzo.
Yeah. Thank you. It's Eliana from Colombia. I just was wondering if have you sorry, it's been a long time since I haven't speak English, but I'm gonna try. I'm wondering if have you catch the difference between meta map with a map training with remote samples. It's too big if I compare with a map that is training with survey samples. It's because sometimes we don't have these survey samples in an opportunity time, in opportune time. So I just wonder if you measured this difference between training a map with survey samples and training a map with or a model with survey samples. It is too big, this difference. That is my question.
Yeah, thank you for the question. This is a good question because you are right that it's quite a challenge to get survey on time during each year if you want a map. If I have understood well, the approach you propose is to use a model that was trained differently on a map or on samples from another year or another place. This is how I understood the question. I would say that it remains very complicated to do that, especially for crops. If you are using data from a past year, the season might have been a bit shifted. So there are methods to shift or to adjust the time series. Atmosphere is not the same between years. So the atmospheric effect might differ and might affect the signal. So it remains complicated to transfer a model from one year to another or from one place to another. It is an active domain of research, and so there are progress every day, every week, every month. So I think that one day it will be possible, but today for operational applications, I don't think we are there.
Okay, thank you so much.
Sophie, I have one. It's one last question for you. You work a lot with complex model and high-tech tools, but what is one low-tech thing you rely, if you rely on one low-tech thing for checking or validating data? Is there anything you could share with us on that aspect?
Yeah, maybe. I mean, when you say that I'm playing with high tech, I would say that we're still using some quite simple classification algorithms. So I know there are a lot of neural networks, etc. And so these are wonderful tools when you have plenty of in situ data. So, but in agriculture, unfortunately, we are not in this in this dream situation. So we have a scarcity of data. So in this situation, honestly, a random forest is doing exactly the same job than the very complex algorithm for less resources. So this is still what we advise is that there is no significant advantage of using a more complex algorithm for classification. But maybe another side of another aspect of the work that does not require high tech is the quality control of the in situ data. So I remember that I've written it on the slides, but I did not talk about it during the presentation. But the data you collect on the ground are always not perfect. So they always contain errors. And I don't know if there are many statisticians in the audience because I don't know them. But I remember that when I was working in Spain, we were working with a statistician there, and he was saying, no, the assumption is that the data that are collected in the statistical survey are correct. This is an assumption, but honestly, if I invite you to go to the field to collect data, and when you come back, there are always errors. So just to say that the quality control of the data is instrumental, it's mandatory, and even if it takes time, and this does not require high tech. So basically, controlling the quality of the data, at least to allow them being used for remote sensing data, for instance. There are some steps that are very simple. Just be sure that the point that you have taken is in the middle of the field, not on the road, because if this is on the road, this is useless. Maybe just checking the point that you have with the NDVI time series to be sure that if the label is maize, that you do not have a grass. This kind of quality assessment, if this is polygons, that the polygons are just closed and not open, so errors of typology, duplication, overlapping, small errors that do not require high tech, but that need absolutely to be corrected to have a good, to be sure that you can really make the best of the data you collected. This
Thanks
is what
a lot,
I would
Sophie.
answer.
Thanks a lot. Lorenzo, then we have one question on the
just
chat.
to say that yesterday we had the chance to compare a bit different type of models from typical supervised random forests. We were going through then convolutional neural networks, temporal convolutional neural networks, down to the new, let's say, innovation that are coming with self-learning algorithms. And eventually we could also provide some clarification on the fact that random forest remains for the time being a very robust algorithm. It deals very well with collinearity and outliers, and it is data intensive, but is less intensive from the resources point of view. So before switching to a deep learning framework, one should consider if there are conditions, let's say, to have a win on that. So we suggest, to start with the simplest algorithm possible and then see if it's worth pushing the boundary to the next level. And we know that if you don't get a very high result with random forest, probably you will not get a higher result just because you switch to convolutional neural network. Thanks.
Thanks, Lorenzo. We have one question on the chat from Freddy Alexander.
Yes, about non-supervised technique. We tried, but for crop type, I would say that this is very complicated to get good results. So non-supervised, if you maybe it will work if you get like in Zimbabwe, maybe unsupervised technique will work to discriminate the sugar cane, because this is a very specific crop patterns, localized irrigation, big parcels, and a seasonality which is a bit different than usual annual crops. So this is 18 months and not 12, for instance. So if you have this kind of difference between the crop types that you want to identify, maybe an unsupervised techniques would work. But between crop types that are in the same season and where the difference is sometimes just 2 or 3 weeks between the peak of the season, or the level of intensity at the maximum is slightly different, but not much, unsupervised techniques will not work, unfortunately.
Thanks a lot, Sophie. So, before we wrap up, then I would like then to extend a big thank you to you, Sophie, for your insightful and engaging presentation. You have a special ability to make such complex topics very clear and really made a difference. Thank you for sharing your experience with us. And also to thank Lorenzo for continued guidance on this workshop, and to inviting Sophie to bring us this important conversation today. Thanks also Gilberto for the participation, since he is part of the FAO team. We truly believe that we had a very good session today, and we will spark new ideas and confidence among the participants. So let's remember that we have an additional reading for the Friday session. Okay, the additional reading was shared on the concept note, and is the activity scheduled for our asynchronous day tomorrow. Okay. Once again, in the name of the Regional Hub for Latin America, thank you for all the participants for your time today, and we see you all again on Friday.
Thank you, and have a good day for you.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
Bye. Bye-bye.